Director of Physics Research Lab in Ahmedabad. It is an honor for Parsec to host this talk. Thank you so much, sir, for accepting our invitation. Dr. Bhardwaj is the chairman of the Joint National Committee of Indian National Science Academy, International Science Council for Research, International Union of Radio Science and Scientific Community on Solar-Terrestrial Physics. He is also a member of ISRO and other national level committees on Planetary and Space Sciences research in India. He has also served as a Principal Investigator in various experiments for many space missions such as Chandrayaan Mars Orbital Mission and Chandrayaan-2. Now I would request sir to continue with the talk. Thank you.
Okay, thank you, and thank you Parsec Astronomy Club at IISER-TVM for inviting me to give this talk, which is essentially on Indian planetary missions. I hope you can see the slides and hear me well.
Yes, sir.
Okay, good. Is to take you to the journey of our exploration in the area of planetary sciences. And this talk is largely based on what India has done in planetary exploration program and what we plan to do in the future. You must have already heard about Chandrayaan-1 Mission, Chandrayaan-2 mission of the Mangalyaan. And I will also tell you about what we plan to do in the future. I belong to a laboratory called Physical Research Laboratory, PRL, in Ahmedabad, which is also called as the Decadal of space science in India. Because this lab is established by Dr. Vikram Sarabhai in the year 1947. And as we celebrate 75 years of independence of India, we are also celebrating the Platinum Jubilee of PRL. And PRL of Physical Research Laboratory has 4 main campuses. We have the main campus in Ahmedabad, which you are seeing probably down on the left side, which is the one which came into existence quite long back. And I will tell you a little bit about that also. We have another campus about 5 kilometers away from the main campus called Aditya campus. We have a solar observatory in the middle of the lake, which is Fadasaga Lake, and this is called Udaipur Solar Observatory. And then in Mount Abu, we have an observatory which is called as Mount Abu Observatory. Now, talking about PRL, as I just mentioned that we are going to complete 75 years of existence of PRL. So we are celebrating it with a special colloquium series, which we call as PRL Ka Vyakyan. And it all started on 4th of August, where we are conducting Vyakyans or colloquium every Wednesday at 4 p.m. So tomorrow also we have a Vyakyan at 4 p.m. You can watch it on YouTube Live of PRL. And as I was mentioning that PRL established by Dr. Vikram Sarabhai, the father of Indian Space Program. And we celebrate the birth centenary of Dr. Vikram Sarabhai just 2 years back. So when I talk about the history of PRL, it all starts with Dr. Sarabhai establishing PRL in a small, in form of a small laboratory, which you see in the bottom left, called the Retreat. This is actually a part of the house of Dr. Sarabhai. And then in 1948, this lab moved to MG Science College. And in 1950, we had the first council meeting of PRL. And the gentleman which is standing here, if you can see it well in the middle of this photograph, is none other than Dr. S.S. Bhatnagar. And in 1951, we started to have the observations from Mount Abu for ozone. So formally, PRL was established on the 11th of November of the year 1947. And we have the building which where I'm sitting right now and giving the talk came into existence in 1954 with its foundation stone laying ceremony happening in 1952. And it was done by Sir C.V. Raman, Nobel laureate. And it was essentially because Dr. Sarabhai treated Dr. Raman as his real guru. And you can see here that stone laying ceremony happening. And in 54, when the building was completed, it was inaugurated by then Prime Minister of India, Pandit Jawaharlal Nehru. And in the bottom right, you are seeing this building right now on 15th of August of this year. As I was mentioning that we have another campus in Ahmedabad, which is called as the Thaltes campus, and an observatory in Mount Abu and Udaipur, which all became part of the development of PRL in 80s. So when we talk about the logo of the PRL, and many of you must be familiar with this logo, which you see here, the circle with the cross in the center is the symbol for the earth. And the circle with the dot in the center is the symbol for the sun. And these two circles are actually encircled by another big circle. And if you translate this logo into a meaning, what it means, PRL research encompasses the earth, the sun, immersed in the fields and reaching from and to infinity, all that man's curiosity and intellect. So this is what we do in PRL. We do research in various fields which are given over here: astronomy, astrophysics, solar physics, atomic molecular optical physics, theoretical physics, geosciences, and planetary sciences. And essentially, what we aim for is to do competitive research internationally and to pursue the excellence. And we have a students program, a doctoral and postdoctoral program. About 150 students are there at the campus at any given point of time. Now, when we talk about how this all fields came into existence and how is been the history of development of PRL in terms of the research activities, you can see that it all started with cosmic rays and advanced science, essentially because Dr. Sarabhai was working in cosmic rays, and the first director of PRL, Dr. K.R. Ramanathan, was working in atmospheric science, a well-known atmospheric scientist. So that's how the two fields started. But in 60s, we brought in theoretical physics and radio physics. In 70s, earth and planetary science, infrared astronomy, and plasma physics. And around the same time, we had the formation of COSPAR and ISRO in 1969, and Department of Space, that is DOS, came into existence in 1972. In 80s, we had the particle physics and solar physics added. In 90s, the laser physics and quantum optics, nonlinear dynamics and computational physics, astroparticle physics and cosmology. And in 86, the plasma physics program in India, in PRL, grew such a large in terms of its size that it formed a separate institute, which we now known as Institute of Plasma Research. So you can see that PRL is actually the mother of several institutes and, in fact, ISRO and DOS, because all activity related to space program of India started from PRL. In 20 or new millennium, we have solar axis astronomy and planetary exploration program added. And then in 2010, decade of astrochemistry, photonics, planetary experiments development, exoplanets, and space weather. And in 2020s, we have ice shock processing, quantum communication, artificial intelligence and machine learning, and ultra-fast laser processing. So these are the broad areas of research which is being done under those 7 disciplines of PRL. And if you look at how PRL has been contributing, you must be knowing about Professor U.R. Rao. He was alumni of PRL. He did his PhD with Dr. Sarabhai and has been the chairman of ISRO and secretary Department of Space. Dr. K. Kasurirangan, which all you must be familiar with, is an alumni of PRL. He did his PhD in PRL and subsequently was the secretary Department of Space and chairman ISRO. Dr. Kalam was actually working in PRL, and then Dr. Sarabhai sent him to Tumba, Trivandrum, where you are all situated, IISER-TVM, and he started the rocketry program there. And then there are many photographs of other gentlemen like B.N. Goswami, director of IITM Pune, R.N. Keshav-Murthy also, R. Sridharan, Director of SPL, VSS in Trivandrum, A. Jaraman, Director of NARL in Tirupati, B. Bora, Director of IPR, and S.K. Singh, currently Director of NIO in Goa. So many directors of various labs has been associated with PRL or are an actual alumni of PRL. Now talking about the today's subject of Indian planetary missions, and you must be seeing some of this photographs down there, which are actually logos of various missions or experiments. And the PSLV rocket, which is basically the workhorse of India, and it has been used to launch the Chandrayaan-1 and the Mangalyaan. And Chandrayaan-2 was actually launched by the GSLV Mark II. Now, when we talk about the solar exploration program, we should also know how the solar system looks like. If you look at this, which we call as the new solar system, you see that there are 4 inner planets, Mercury, Venus, Earth, and Mars. And then there are 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. So these inner planets are much smaller in size compared to these outer planets. And inner planets are also called as terrestrial planets. Terrestrial means Earth-like, basically because they have rock on their surfaces. But if you go to outer part of solar system, they are called as gas giants or icy giants. Jupiter and Saturn are gas giants. They don't have surfaces. It is all gas or liquid. And Uranus and Neptune are icy giants, and they are much bigger in size. If you look at the number of satellites in the inner part of solar system, Earth has 1 moon called the moon. Venus doesn't have, Mercury doesn't have. Mars has 2 small moons, Phobos and Deimos. But if you go to the outer part, Jupiter, Saturn, Uranus, and Neptune, each one of them has more than 25 to 30. In fact, Saturn has more than 70 now. So that means outer part of our solar system is much different than inner part of solar system. And in addition to this, we have many other objects like Ceres or Fume, Makemake, Eris, and Pluto. In fact, Pluto is now called as dwarf planet. And in fact, this is an exercise to all of the listeners who are listening to this talk, why Pluto is not considered among the classical planet in our solar system. We also have other objects like comets and meteorites, and they are also very interesting because they contribute in terms of understanding the evolution of a solar system. Now, if you look at this 4 terrestrial planets, Earth, Venus, Mars, and Mercury, you will say Earth and Mars is both roughly same in size. Mercury is half. Mars is half and Mercury is 1/3. But if you compare them with the outer part, you will say that Earth is the 5th largest planet. The biggest is Jupiter, then comes Saturn, then come Uranus and Neptune. But if you compare them with the Sun, then you say that Earth is very small dot in front of Sun. And on that dot, on the Earth, where is Trivandrum? And that inside Trivandrum, where is ISER? And then wherever you are sitting. So if you see the size of the Sun itself, it is huge. Okay. So that gives you a just feel of the dimensions when we talk about the solar system exploration. Now, all activities of exploration started with rocketry program, as I was just mentioning that Dr. Kalam was sent to Tumba in Trivandrum to start the rocketry program. And we have the first rocket launch from Tumba in November of 1963. And it has experiments of space sciences. They were all developed in PRL in Ahmedabad, and they were launched from Tumba. Subsequent to that, Professor Rao was sent to Bangalore, and he started the satellite program. And we have the first Indian satellite Aryabhatta launched in the year 1975. And that carried also experiments of atmospheric science and astronomical science developed in PRL. Subsequently, we have many other missions like SOSC, SOSC-2, IAXE, and SOX in the years of 80s, 90s, and 20s. And they were all looking at astronomy, atmospheric science, and space sciences. But the first planetary mission of India is the Chandrayaan-1 mission. Chandra means moon, Yaan means spacecraft. That's how the word Chandrayaan-1 has come. And this is the name given by then Prime Minister of India, Atal Bihari Vajpayee. And he said it should be Chandrayaan-1, not Chandrayaan, because you should have series of missions to move. We had the launch on 22nd of October of the year 28, and we reached the moon after 16 days on 8th of November. And this was actually a truly international mission because we have 10 countries participating with 11 experiments on board, and 3 of them were being flown for the first time to probe any planetary body. If you see this picture on the right side, you will see all the various experiments of payload situated, and you can see much better over here. We call them payloads because we pay and load them. Otherwise, they are basically experiments which brings science. And I was involved in an instrument called SARA, which consists of 2 sensors, SWIM and SINA, situated on the top deck of the Chandrayaan-1 mission. And we have the moon impact probe sitting on the top deck of this Chandrayaan-1, which was actually released from the orbiter, and which landed very close to the South Pole and provided a very good amount of data about the dynamics of how we can do the landing. There are many science results which has come out from the Chandrayaan-1 mission, but of course the most important has been the discovery of water on the moon. Till that time, we were all thinking that moon is bone dry. There is no water on the moon. But now we know that moon has ample amount of water. It is there at all the places. It is much more in the polar regions and particularly in the permanently shadowed regions. There are many other science results which has come out in about 180 scientific publications, including, of course, water presence beneath the surface, above the surface, large expanses of crystal feldspar, which essentially talks about validating the lunar magma hypothesis, or essentially telling about how moon came into existence, talking about mini magnetosphere or discovery of mini magnetosphere, various craters of various dimensions, and volcanic activity, which in fact, in terms of geological time scale, is as recent as 100 million years or even down to 10 billion years, which in turn suggests that moon is geologically active. And then, of course, a couple of rallies which can be used for habitat. And many of these scientific publications has formed the cover pages, like, for example, of Science or Geophysical Letters, which talks about discovery of water or discovery of mini magnetosphere on the moon. This is the picture which I like very much, which is how the Earth looks from the moon. This is taken by Chandrayaan-1 terrain mapping camera on 22nd of July of 2009. And this was the day of eclipse. So we were more interested to see the shadow of the moon falling on the Earth. And that is how we rotated the whole spacecraft to look back at the Earth. And unfortunately, which you see over here, there's a lot of clouds, the white patches we are seeing on this globe of Earth, and which did not allow us to see exact shadow falling on the planet Earth. But of course, it gives you a feel of how the Earth looks like from the moon. Now, let me take you to journey to Mars, and using the Indian MOM. So, Indian MOM is in orbit around Mars, and it has launched on 5th of November of the year 2013. And after 10 months of journey, on September 24th of 2014, we reached Mars. We got inserted. And since then, we have been in orbit around Mars. So, MOM mission or Mangalyaan is still in orbit around Mars. It is working. And it has been working for more than 7 years now, though the planned lifetime was just 6 months. And this is a rare feat for India, essentially because India is the only country in the world, which is able to successfully insert an orbiter around the Mars in the first attempt. No other country has done it. Okay. Now, this mission has 5 experiments on board, and this gives you just a feel about. Are you able to see my slides and view it well, right?
Yes, sir. Everyone, it's visible.
Okay, good. So what you're seeing over here is how we departed from Earth, where the Earth was when we departed from Earth, and where the Mars is. And now the Mangalyaan or the MOM mission has to move from Earth to Mars. Mars is moving, Earth is moving, and the MOM is moving. And you have to capture an orbit into the Mars after reaching very close to the Mars and get inserted. So these are the very technologically challenging things where you have to maneuver the spacecraft perfectly well so that you reach at the right time, at the right place where the Mars is, and then only you can get inserted. Otherwise, you will miss it. Okay, so these are complex processes which is done. Now there are, as I was mentioning, there are 5 experiments on board. Total weight is about 13 kg, whereas the total spacecraft mass is 1.3 ton or 1,300 kg. So essentially, the experiment mass is hardly 1% of the total mass of the spacecraft. And we had mass color camera, methane sensor for Mars, thermal infrared imaging spectrometer, Lyman alpha photometer, and MENCA. And MENCA is an instrument which I developed when I was at SPL and VSSC in Trivandrum. And these are working very well. They're all accommodated on the spacecraft at different locations, which you see over here, depending upon their science requirements. And from the Mars color camera, we now had very large number of this full disk images of Mars. And this is how the Mars looks like, where you can see, in fact, the North Pole on the top or the South Pole in the bottom. And this is at a different season, where you see the freezing happening on the North and South Poles. And you can see much clear the features on the surface of the Mars. One can also see Phobos passing in front of Mars. You know, this black dot which you see over here moving on the top right side is nothing but Phobos, which is a satellite of Mars. And this was captured by the Mangalyaan. We also have got a very good idea about many other features on the surface of Mars, including valleys of Marinus. This is one of the biggest canyon in our solar system. It is much bigger than the Grand Canyon. And here you see it completely filled with dust and clouds. These are actually clouds which you're seeing here elevated, but you can see it much better in another picture, which is taken at different time, at different seasons, where you can now see this valleys of Marinus. It is quite deep. It is 4 to 5 kilometers at places and quite long in terms of its size. There are many science results which has come out. I'm not going to detail of each of them, but of course to tell you particularly for MENCA, my instrument, where we actually got first information about how a carbon dioxide dominated atmosphere changes to oxygen dominated atmosphere as you move up in the atmosphere. So this came from the evening time atmosphere of the Mars, where we have the orbit of Mars going around from the dawn side or morning side and coming out from the evening side. And we had the observation which suggests that Mars, which is actually dominated by carbon dioxide, about 95% is carbon dioxide in Mars, converts or transforms to an oxygen dominated atmosphere somewhere around 250 or 260 kilometers above the surface. And that is the importance of this science, that you have the conversion of carbon dioxide, which essentially dissociates into carbon and oxygen starts dominating at higher altitudes. We have also found, suprathermal argon in the exosphere. Exosphere is actually a region of, or the upper region of that atmosphere where atoms or molecules don't collide. So essentially what it means is that once you have little higher energy atom or molecule, it will escape. It will escape the planet. And this is what we have found, that argon, which is also about a few percent in the atmosphere of Mars, has 2 different temperatures or 2 different energies. And those which have little higher energies will be easily escaping the Mars, which in turn means that we have to now relook at how the escape of the atmosphere of Mars is happening and try to look at its energy budget and constrain various models. So that is the importance and implications of these results. We have also seen many cloud formation at the leeward side of the mountains. In fact, Mars has the highest mountain in our solar system called as Olympus Mons. Olympus is mountain. And on the leeward side of that, we see the cloud formation, which you're seeing here in this picture. We also seen Deimos. Deimos is another small satellite of Mars. And because of the orbit of the MOM becoming quite elliptical, we are able to go back side of the Deimos and see its structure. And this is the first information which came in January of 2016, where we are able to see how the Deimos looks like using the Mangalyaan mission. When the Mangalyaan mission became famous after the insertion of the orbit of the Mangalyaan in the Mars, one of my colleagues from US sent me this photograph and says that the MOM mission, that is the Mars orbiter mission, has become so famous that it has come on the Coke night. And Google, celebrated the success story 1 month later on October 24th of the year 2014 with its Doodle. And it's Amul, which you may be knowing is a lead brand of milk products, and they come out with ISRO's cow Amul ye cheez badi hai mast Mars. So that is how the country was celebrating this rare feat. And National Geographic magazine brought on the cover page the pictures taken by the Mangalyaan. And Government of India, realizing that this is really a scientifically and technologically feat for India, has put the Mangalyaan on the back of the 2,000 rupees. I hope most of you must have noticed that on the back of the 2,000 rupees note, we have the photograph of the Mangalyaan. Now let me go to Chandrayaan-2 mission, which is the second lunar mission of India. And this is much more complex and complicated compared to Chandrayaan-1 mission because it had Vikram lander, and inside the lander we had a rover. So in addition to orbiter, we had a soft lander called Vikram, and inside the lander was a rover. And we had everything going perfectly well. You are all aware about it, that we had launch of the Chandrayaan-2 mission in the year 2019 in July. We got inserted into an orbit around the moon and then went down to 100-kilometer polar circular orbit. And subsequent to that, on September 7th morning, early morning of the year 2019, we had the landing of the Chandrayaan-2. We could not do perfect landing, and but it had been a success story in many sense because it provides very crucial data, which has now been used to devise the next mission, that is the Chandrayaan-3 mission, which will be a lander and rover mission. On the Chandrayaan-2, which is an orbiter, it is working very well in orbit around the moon, providing excellent quality of data. It has 8 experiments on board, which is now providing information about the different terrains, geological features, producing 3-dimensional map, supporting elemental composition using XSM, which is an instrument developed in PRL, identifying the distribution of various geological features in terms of mineralogy and distribution of water on the surface, looking at various features beneath the surface using dual frequency SAR. SAR stands for synthetic aperture radar. So we have a L and S band SAR, and that is providing information beneath the surface to several meters down. We have CHASE-2, which is providing information about the distribution of very tenuous atmosphere, which we call as lunar exosphere. And the Rumbar dual frequency radio science experiment is providing about the total electron content, or essentially the plasma environment around the moon. As I was mentioning that we are now going to have the Chandrayaan-3 mission, which will be more or less similar to Chandrayaan-2 lander and rover mission. And on the lander, we have 3 experiments. Lemur probe, which is a part of the Ramba. Chaste, which is essentially, you can say, a thermometer going inside the surface of the moon to probe the temperature profile up to 10 to 30 centimeter beneath the surface. Okay. So we are essentially trying to understand how the heat transfer takes place from the surface to inside the moon. And ILSA is an instrument which will provide us information about the seismology or seismic activity. There are 2 experiments on the rover. Rover is going to come out from the lander and move onto the lunar surface. And on this rover are 2 experiments. One is LIPS, other one is APXS. LIPS will be providing us information about the mineralogy and chemical composition of the lunar surface. And APXS will provide the elemental composition. It is alpha particle access spectrometer, whereas LIPS is laser-induced breakdown spectroscopy. So APXS will provide us elemental composition, whereas LIPS will provide you mineralogy and chemical composition. So these two instruments will complement each other, and it will provide information or ground-truth information about the elements and minerals present on the lunar surface in the regions where this rover will be moving. These are some of the information which has come out in terms of science results from the Chandrayaan-2. What you're seeing here is the terrain mapping camera for 4 are there enough, essentially because it has 3 viewing direction, and using that it can generate the DEM or digital elevation maps. And one can get a lot of information, for example, this crater, which is the Sarabhai crater. In fact, Sarabhai ji has a crater on the moon, which is named after him. And this crater has been mapped by the Chandrayaan-2 very well. This is situated on the near side of the moon. So if you look the moon with a big telescope, you can actually see this crater because it is at 24.7 degree north and 21 degrees east. And it is about 8 kilometer in diameter and about 1.7 kilometer in deep. So this is actually ortho image DEM of TMC-2 of the Chandrayaan-2 mission, which is giving information about how the Sarabhai crater looks like. Or you can see craters of different other known features like Lindbergh here over here, which also says that how the crater distribution is there on the moon. You can see on the walls of this crater itself, you have craters. And there are craters of various dimensions, right from centimeters to meters to kilometers to 10 to hundreds of kilometers and to thousands of kilometers. So moon is actually full of craters because moon doesn't have atmosphere, and any particle which is coming towards the moon will hit the surface and form a crater. So that's why the moon is full of craters, and you can see craters inside craters, craters outside craters, here crater, there crater, everywhere crater and crater. And we can see these features in the SAR images. The craters which are buried beneath the surface also can be seen using the SAR instrument, which is a dual frequency. Here you're seeing the habitable images. And one can actually get much closer view using OHRC, which is actually optical high resolution camera on the orbiter. And you can get information about this boulders, which is very important because when you do or plan a landing mission, you should see that the terrain is very smooth, not much of a slope, and there is not much boulders, because if any of the leg of the lander comes on the boulder, then there is a chance of toppling. So information related to small boulders to big boulders has to be there, as well as, of course, the craters. Solar X-ray monitor, which is an instrument developed in PRF, is now providing us information about the X-rays which is falling onto the moon. And this is the most sensitive instrument flown so far by any country. And it has the highest energy resolution and providing a spectrum of 1 to 15 kV every second. And it has shown that there are micro flares which is happening on the moon, which has not been seen by any other instrument so far. And it could detect almost like more than an order of magnitude below what can be seen by GOES instrument, for example, of NASA. So this instrument has now shown us that there are many flares, which we call as micro flares or sub-A class flares happening on the sun, and more particularly from a region which are not active. What it means is that there are flares happening from a known active region or region which are not active, because we know that flare happens from the region which is active. But we are now seeing flares happening from a known active region. And these are small flares which can actually pump in a lot of energy into the corona of the sun, which could be one way to maintain the 1 million Kelvin temperature of the sun, of the corona. And that is how this science results, which got published in Astrophysical Journal Letters, there were 2 of them, made the press releases by ISRO, and then of course was captured by a lot of media both within the country and outside the country. We also have an instrument called CHASE-2, which is a sequel to the CHASE-1 instrument on Chandrayaan-1, where we are looking at distribution of various gases in the atmosphere of the moon. Of course, moon doesn't have atmosphere, but it has a very tenuous atmosphere, almost perfect vacuum, you can say, with respect to Earth. But densities are of something like 10 to 4, 10 to 5 particles per cc. And we were interested to look at what happens to argon-40, because argon-40 is a decay product of potassium-40, which is a radioactive element. And we wanted to see its distribution right from equator towards the pole, and from sunset to sunrise to back to sunset. That means diurnal variability and latitudinal variabilities. And this suggests that the abundance of argon-40 is highest at the sunrise and sunset time, and it is minimum during the sun daytime, that is noon, and in the night. And this is also a unique information in terms of its distribution, because what we are seeing on the moon now, that argon-40 has large variability, number one. Number two, it has patches of higher concentration, which of course is not shown over here, which suggests that there is something intrinsic happening on the moon surface at certain location, which is providing a much higher abundance of argon-40, or you can say the higher concentration. Okay. And that is the new information which has come out from the Chandrayaan-2 mission. What next? We are now talking about mission to Sun, Aditya L1 mission. Aditya means Sun, and L1 is the location, and I will tell you about that. So this is the first Indian solar mission. Of course, it is not going to the Sun, it is going to L1 point. And we have instruments which is going to look at the Sun in the visible, in ultraviolet, and in soft and hard X-rays. In addition, we also have instruments which look at the charged particles which comes out from the Sun all the time, using instruments and to look at their energy distribution and the composition. So we have remote sensing instrument working in visible, ultraviolet, and X-rays, and we have charged particle detector detecting in situ the charged particles. And our idea is to understand the coronal heating issues, solar wind acceleration, understanding the flares and coronal mass ejections, which are violent activities which affect the planet Earth also, and how to understand the coupling of different regions of the atmosphere of the Sun, right from photosphere, which is at 6,000 Kelvin, compared to corona, which is at 1 million Kelvin. And of course, the distribution of these charged particles, the solar wind which is coming out of the Sun, how does it accelerate, what is temperature distribution, and why do we see anisotropy. Now, talking about the L1 point is the point between Sun and Earth. You see here in the center the yellow circle, which is the Sun, and Earth is in the light blue. And L1 point is a point on this line, about 1% distance away from the Earth on this line. So it is 99% away from the Sun and 1% away from the Earth. The beauty of this point is that L1 point goes along with the Earth in its orbit around the Sun. So as Earth is going around the Sun, L1 point also goes around the Sun. And that means one gets an uninterrupted view of the Sun all the time. So that is the biggest advantage, that you don't get eclipse. If you are going around the Earth, you will at point or sometime will not be able to see the Sun. But that is not happening when you are at L1 point. So using the Aditya L1 mission, we are going to the L1 point, and that is going to be a very interesting mission from India, because we are doing remote sensing in 4 different bands, as well as in situ measurement of charged particles. In future, we are planning to have a mission to Venus, as well as a second mission to Mars. Now, when we talk about mission to Venus, Venus is a very interesting planet. Venus is very unique also. Right now, what you are seeing here, this image of Venus is not of the surface. This is actually clouds, because we cannot see the surface of Venus. Venus is full of clouds of sulfuric acids, completely covering the whole globe. And what you are seeing here is actually the strides or clouds movement. Whereas in case of Mars, which is seen over here, this is the image from our Mangalyaan, you are able to see surface features, right? So Venus has a very different circumstances. Its composition is carbon dioxide, like Mars, so it is CO2 dominated atmosphere. But the surface pressure of the Venus is about 100 bar. 100 times the surface pressure of the Earth. If you look at Mars, it is 100 times smaller. So now you have two planets, one inner to the Earth, one outer to the Earth, both dominated by carbon dioxide. One surface pressure is 100 times more than that of the Earth. Other fellow is 100 times less. Okay. Now talking about temperature, the Venus surface temperature is about 800 Kelvin, or you can say 400 degrees centigrade. So the surface of Venus is very hostile. It's really a hostile place to go. But if you go something like 40 to 50 kilometers above the surface of Venus into the clouds, you see that temperatures are very benign. It is something like 25-30 degrees centigrade. And the pressure is about, so that means the atmosphere of Venus, particularly the clouds, are at very convenient and benign location. And that is why people are now talking about possibility of life on Venus in clouds. Whereas people talk about the life on Venus, on the Mars, on the surface, because surface of Mars is quite conducive, whereas surface of Venus is not at all conducive. It is very hostile. So now we have two planets, Mars and Venus. Mars, we have done the exploration, and we plan to do the exploration of. Now, Venus has also another peculiarity. Venus rotates very slow. It completes its rotation on its axis in 243 Earth days. That means you will have something like 120 days day and 120 days night. So that means you have to work very long and then sleep for a long time. Okay. But if you look at the atmosphere, particularly the clouds, they complete its revolution around its own planet in 4 days. That means atmosphere is super rotating. So there is super rotation happening on the Venus with the 4 day compared to 243 Earth days. And that makes also Venus very interesting and very different than any other planet in our solar system. So we are targeting to explore Venus in more detail because it has not been explored in that much detail as compared to Mars. Now talking about these planets, I will tell you that PRL has discovered exoplanets because we have a program of astronomy where we look at exoplanets. And this is the first discovery of exoplanet from India about 3 years back, where we discovered a sub-Saturn size exoplanet using our own instrument called PARAS and using our 1.2 meter telescope in Mount Abu. This exoplanet is rotating on around its star in 20 days. It's about 6 times the size of the Earth, about 27 times the size of the mass of the Earth, and it is about 600 light years away. Okay, and this being the first discovery from India, our Prime Minister Narendra Modi ji, in fact, tweeted and congratulated the scientists of PRL, telling that immensely proud of our scientists who created history by discovering a sub-Saturn sized planet 600 light years away from Earth. Congratulations to them. The discovery puts India among select countries because India is among the first few countries in the world who have discovered exoplanets. And this was done using the telescope at Mount Abu. You see here the picture of this telescope, which is 1.2 meter telescope at a height of about 1.7 kilometers. And this is the best site in western part of India because it has almost like 200 days of free nights or cloud-free nights. And it is somewhere close to the height of Ponmudi, close to Trivandrum, there's a hill station called Ponmudi, which is about 1100 meters in height. And but it is better compared to Ponmudi because Ponmudi is quite most of the time. Whereas here we get almost like 200 days of cloud-free nights. And now at this same location, they are coming with their 2.5 meter telescope, which you see over here in this picture, which is almost ready and now getting commissioned. So probably next year, early next year, we'll be able to use this telescope to make observations. And it will provide us almost like factor of 10 improvement in terms of its sensitivity because of its larger size, as well as the instruments which are being used there. So if one of you are interested, you are most welcome to come to PRM as well as to Mount Abu to make such kind of observations or even for a visit. So with this, I would like to thank you all for listening patiently for this talk. And if you have any questions, you are most welcome. Thank you very much. Hello.
Yeah, hello, sir.
Are you able to hear me?
Yeah, hello, sir.
Yes.
I had a question. So as we know, the craters on the moon are formed by the impact of asteroids and meteorites on the moon. So have you observed any major composition differences between the crater and the other parts of the moon?
Yes, of course. If you look at the mineralogy of the surface of the moon, it varies from location to location. It depends upon when this crater has been formed, which is called as dating of the crater, and how essentially means how young or how old the crater is. Number one, and number two, what kind of impactor has created this crater. So both this information can be derived if we have a payload or an experiment which can sense the changes in the chemical composition or mineralogy of the surface. Using Chandrayaan-1 also we have seen that there are compositional changes at the surface of the moon and also of the craters. So this information is known.
Yeah, thank you.
Hello, sir. I have a question.
Yeah.
Sir, in starting of the talk, you have talked about the research in PRL going on quantum communication. So, can you tell us more about the future prospect of quantum communication and what are the research going on this field in PRL?
Quantum communication work has been going on for quite some time in PRL. Essentially, as a part of photonics and laser physics work, we have developed an entangled photon source, which is the essential requirement for quantum communication, and also developed technology for QKD, or basically quantum key distribution, which is a basic requirement for having a quantum communication. We also demonstrated this over 200 meters that it works, and we are now interested to develop a payload or an experiment to fly in space to demonstrate this in terms of its functioning in space. Essentially, there is a group who is working on this. If you need more details, you can go to Atomic Molecular and Optical Physics Division, and in the PRL website, you will get some of the details as well as the scientists who are working on that and get further details on it. But our idea is essentially to develop this technology within the country and then to use that for space-based quantum communication.
Thank you, sir.
Hello, sir.
Yes.
Sir, so in one of the slides, there was a spectrometer which was measuring for argon 40, the of argon 40. So why argon 40, and what does it mean if the abundance dependence?
Okay, argon, as I was mentioning, argon 40 is a decay product of potassium 40. Okay, it's you can say isotope. Okay, and argon is a inert element, right? Like helium, argon, kind of thing. So inert elements don't react or don't have chemistries. And secondly, if you see argon on the moon, it is believed to be of native in nature. Essentially means that it doesn't have any contamination from Earth or any object which goes from Earth. So they are treated as pristine in terms of the nativity. And therefore, if you look at the distribution of such what you call elements which are inert or which are elemental, they provide you a lot of information actually of the object. And argon-40 is very unique because it is what you call volatile in some sense, but it condenses or it evaporates when it is sunlight or or midnight. That's why its distribution looks to be very funny, because it is peaking at sunrise and sunset time, but in the noon time it is low, and in the midnight also it is low. Secondly, the distribution is seen to be patchy, which of course I did not show you on the globe of moon. But what we have found out that there are locations where argon is much more in abundance. So that means there is something happening on the surface or beneath the surface, which is having a very different argon composition and distribution compared to the other locations. Now this has linkage to the moon and geology of the moon and the formation. And that is why we are looking at the argon-40.
Thank you, sir.